Hey everybody. So I just wanted to point something out to you before we get going on this lesson. Last week we covered these two things, or for the last set of videos, and I was able to get to everything in here due to the fact that we're not doing this in class. I was actually able to teach systems of inequalities in the set of videos that I did, and so we don't need to do this lesson for this week because we already did it in the last set of videos at the end of the video. Um, so all we're going to focus on in this video is the Gauss-Jordan elimination. And so we're going to talk about matrices today, and I'm going to give you some examples, and we'll make these videos kind of short so that you have time to watch a video and then go back and you can see it again. So with that being said, what you do with matrices is you convert a system of linear equations into an augmented matrix. So for instance, if I go to this and I give you the following, let's say you have y, you have x is equal to 1, and you have 2x minus 3y is equal to 4. We can convert this. This is a system of equations. You guys would probably solve it by elimination, but we can convert this to what's called an augmented matrix. And all you do is you take the lead coefficient of each variable and you write them into this thing called a matrix. And it has this little line to indicate where the solutions are. Not always does it have that line, but if you're going to solve a system, it will. And then we're just going to write the coefficients. So since x is 1 and 2, we have a 1 in the first row, a 2 in the second row. And then we have a 1 in the second row and a -3. Make sure you watch the signs. And then we have a 1 and a 4. And so this is the augmented matrix for this system of equations, and I'll give you some more. You can have the following. We can have y is equal to 4, or we can have 2x plus 3y minus z 1, and then we can have x plus y is equal to -4. Let's say we have those. And so if I wanted to do an augmented matrix for this one, 3 by 3 in this case. Let's do this equation first because that will be easiest. So we can write 2, 3, -1 for z, and 1. Okay, so I've just taken the coefficient from each. This is x, this is y, this is z, this is what they're equal to. The next one, let's do this equation. So there are no x's, so that we're going to put a 0 here. There is 1y, so 1y. Lead coefficient here is 1. And then there's no z, so we put a 0. And then we put a 4. And then finally we have an x, so there's 1x, 1y, no z, so 0 z's, and -4. Okay, and so with that being said, this is the augmented matrix. And we can use that to do Gauss-Jordan elimination, which we'll do in another video. We won't do in this one. I'm just showing you how to set these things up. So realistically, guys, if there's no variable for something, you put a 0 there to indicate that that space is filled with a 0. Those zeros become very important in solving these things, and so hopefully we'll get the rules down and we can get you guys going on this. Okay, so let's look at this next thing. We have reduced row echelon form, so RF. And what it says is all lead coefficients are 1. So what that means is if you have a 1 here, if you have a 2 by 2, this is the lead coefficient, this is the lead coefficient. Those would be your lead coefficients being 1. This is in RF form. It says all rows of zeros are on the bottom. So for instance, if you have this 1, 0, 0, 1, 0, 0, 0, 0, this is what it's talking about. If you have a row of zeros, they go on the very bottom of the matrix. You can move the rows around. You can swap them however you want. You cannot swap columns, however, so don't swap columns. You will screw something up if you switch the columns, like if you switch these two. But if you switch the rows, you should be fine. Okay. Each lead coefficient is along the diagonal. So the diagonal is right here. Okay, those are where the lead coefficients are found. That's why I knew to put 1 here, 1 here, 1, 1. If there was a 1 in this row, it would go here. That would be your lead coefficient for that case, but it's not. And then finally, all numbers above and below are zeros. So you can see that all numbers below this one are zeros. Above and below this one is a 0. And above, well, there's no 1 here, but in this case also, below is a 0, above is a 0, still works. They can get bigger. You can have things like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, or 0. Okay, this would also classify as RF form. Another way to classify as RF form would be the following: 1, 0, 0, 0, 1, 0. Actually, let's do this. 0, 1, 2, and 0, 0, 0. Okay. This is still in RF form, so I hope that helps you guys understand.